All right, welcome back. So, I guess just some reminders that homework B1 and Lab 2 are available. Lab 1 is due this upcoming Sunday. Um, we're now moving into chapter 2, so ideally read that before lecture B2. But the only real assessment we have on whether you read chapter 2 is this ICA. So really, it's up to you on whether you take that ICA. The ICA should be available already, due before lecture B2. It's just 5 questions and covers basic sim concepts that we'll start to introduce today, and that you should have seen on that first lab that you've been working on. Any questions? Everything okay? Monday is a holiday, so the TA will not be in lab for Monday, as the announcement was just announced. But the lab will be open Tuesday, and the normal lab 2 will be due a week from Sunday. So we couldn't perturb the lab schedule just because lab happened to land on a Monday this semester. All right. Okay, so we talked about modeling in general last time, and now simulation modeling. So I mentioned last time that industrial systems engineers sort of build knowledge about these complex systems that for which there really is no other discipline to kind of lean on. So we have to hopefully pull from a bunch of different disciplines that integrate, but also have to do our own experiments, do our own inference, and our own modeling. And so, we have to build models. We have to make inferences about models. We have to study models. So models are ways in which we can gain insight and test our intuition, to test our ideas about how systems work. And so we define models. So we said there's fashion models, there's animal models, there's models in physics, like the models of electron here. And the sort of the thing that these all have in common as that they are answers to what if questions. This is also my definition of what is an experiment. An experiment is something that helps you answer a what if question. It helps you test a prediction. A prediction is always an if then statement. So an experiment actually tests to see if the then that comes after actually matches what really comes out. Then a model is the same thing. So just like running an experiment, running a simulation model, you're going to be saying, I have arranged things in this particular way in my simulated airport, in my simulated manufacturing system. Are things going to work out the way that I'm hoping they're going to work out? I run that sim, and then that tests my what if. That sort of generates an outcome. And if it isn't the outcome I expected, then that suggests that my concept of how things were going to operate isn't quite right, and I need to refine that and redesign that. So what I mean by models answer what if questions. So there's a bunch of different types of models. Models can be simulation models like we'll build here. Models can also be out in the real world. The Titanic is a model of what happens when certain metals and combined with certain temperatures of water and salinities of water, and in the context of transporting people and things around the globe. And that, is a very costly model. And hopefully the models that we build in sim are not quite as costly. So, and on top of that, by building a model in sim, hopefully it becomes more generalizable. What happened with the Titanic was very insightful, as much as it was catastrophic, but it may have been, the knowledge gained from it might have been very narrowly scoped to these exact situations. Whereas if we build a model in sim that isn't quite as specific as this one, maybe drops out some of the details, in some cases, we lose the ability to predict exactly what might happen in this particular situation. But in other cases, we actually get more generality. We can actually gain more insight around a wider range of logistics problems when it comes to the open water. So reducing realism is not a frailty of models. It is not our goal to make the models as realistic as possible. It's to make them as insightful as possible. And counterintuitively, taking details out of models often allows us to gain more insight, because we can focus on the things that we care about. And, in general, what happens when you put, if you're talking about fast food restaurants or whatever, when, if you put windows in sequence or in parallel, in general, I want to know the effect of, sequential windows versus parallel windows. Well, rather than modeling a specific fast food chain, if I can model somehow a generic fast food chain, then maybe my results will actually apply to a wider range of them, rather than if I model some, a specific McDonald's on a specific corner of Phoenix, I might get results that match that particular McDonald's on that particular corner, but there might be some weird idiosyncrasy of that particular McDonald's that has nothing to do with the general feature that I'm looking at, and more to do with the specific case of just for that particular McDonald's with that weird other aspect of that restaurant, when combined with the thing I'm trying to study, gets this result that is interesting, maybe in an academic perspective, but not generalizable. So reducing realism helps to actually increase generality in many cases. So, that's kind of where this class lives, is trying to figure out how to build these simulation models using tools that we get from mathematics, statistics, and programming that are just the right balance of realism and generality, so that we can gain the most insight. And so it's going to, our big challenges here to get that insight will be, how do we not only get the most insight out of this, but how do we do it in a model that actually runs in a reasonable amount of time? The types of models you're going to build in this class are not going to be so big that it's going to take weeks to months to run. But in real simulation systems that do get very complex, then it may take an hour when you hit run for one replication to run. And if you want to run 10 or 100 replications, you might need quite a lot of compute time. So either multiple computers running in parallel or a whole lot of time at one computer. And so part of the thing that we'll address in the back half of the class is how do we find ways to get the exact same statistical power out of a fewer number of simulation replications in order to do this. So, I do research that has to do with simulating how water flows in a river basin in Texas that stretches across all of Texas, and simulates where to put wetlands all over Texas in order to best benefit the locals there in terms of both flood resistance and drought resistance. And we run these complex models after we try wetland scenarios. And each one of those replications just takes 10 minutes to run. And we have 900 different places we can put wetlands. And so there's 2 to the 900th different ways we could design these wetland configurations, each one of them taking 10 minutes to simulate, with a model which may or may not be a great model of what's going to happen in real life. So 2 to the 900th is a really big number. And so part of our challenge is to figure out which of those wetland configurations to run, because we can't run them all. So that's what I mean by reducing execution time and figuring out kind of the best way to get the most insight out of this. And that's going to require a lot of statistical methods. And so we will, get a chance to practice our experimental design in this class, to practice our inference methods, and to maybe introduce some inference methods you haven't seen or didn't notice the first time they went by in 380 or 385. So that's a rough overview of where we are. We're going to take all of that, cram it in to these 15 weeks, 30-ish lectures. And so obviously we can't cover everything. And so if there are things that are particularly interesting to you, like statistical methods or how to actually write the sims, or the mathematics involved in these things, then as you continue in the lifelong learning process that is an engineer, then there are ways to, there are actually whole classes in grad school that focus on just one of these bubbles. And so, there are simulation specialists that focus on just the stats of sim, or just the math of how to model these systems, or just how to build programming frameworks so they're most efficient for this. And some of these are more IE like, some of these are more CS like, but we try to sample from all of them in this course, but it is really just a survey of the intersection of these methods. But practical sim, you can go off in each one of these directions independently as well. So it's a very rich area. Okay. So any questions about the motivations or anything? Does everybody understand what I mean by what ifs? Or you maybe start to buy the idea that models that are less realistic sometimes are more generalizable, or any other general questions or concerns about the class and its structure? Okay. All right, so SIMs. So we focus on modeling generally, specifically SIMs. And so simulation models, one type of quantitative model. Quantitative model, they're much better at dynamic change and things like that, but they're very limited in their kind of experience of the world. So they only kind of know as much as you put into them. The three big groups here, agent-based modeling, system dynamics modeling, and discrete event system simulation. This is our big focus, DEF. But there are other courses we teach, like 477, that focus on system dynamics modeling. System dynamics modeling you see in the business community quite a lot. So at WP Carey, they teach courses on SDM, system dynamics modeling. In sustainability, they teach courses on system dynamics modeling. So in the sciences, they do a lot of system dynamics modeling. And then also we've got courses here, IEE. So, and then agent-based modeling is much more, it's more commonly seen in the sciences, but now it's starting to show up more and more in engineering context. So just want to give a quick, overview of these three different methods before we kind of commit to one of them. So I mentioned system dynamics modeling. It's used in a bunch of different disciplines. You can find courses on it all over ASU's campus and different colleges. And it basically models the average or macroscopic behavior of complex systems. And so we're modeling sort of averages over usually long time periods, as opposed to the variations you see from day to day to day. So it's trying to understand how basic causal interdependencies explain consistent trends. So if it's generally the case that A causes an effect on B, and B causes an effect on C, and C has a feedback back to A, then at any instant of time, A, B, and C could be doing anything. But generally speaking, that causal structure is going to cause A over time to decrease, or B over time to increase, and so on and so forth. Those are the types of things that are being studied in system dynamics modeling. You aren't modeling individuals. You're not modeling that level of resolution. You're usually modeling groups or demographics. And I'll show you examples of that here in a second. The advantages of this, because you're not modeling fine scale details of the world, they're very fast to simulate. They basically are doing numerical integration of differential equations. And so it's a lot like when you first learn calculus and you learn that a derivative is actually approximated as a slope at small time periods. Well, that's basically the causal dependencies are written as derivatives, and then the computer program zooms in on a small time scale where it approximates each one of those derivatives by a little slope, and then numerically integrates all those slopes. And so it's a very simple kind of process to numerically go from an initial condition to a trajectory, an approximate trajectory. And that's what's going on behind the scenes. But the strength of these models is you don't actually have to write the differential equation. They've built user interfaces that allow you to draw diagrams that look like this one. That if you know how to read them, you can translate this into a differential equation, but you don't have to. So you can have people who don't have a mathematical background draw these so-called stock and flow models and hit play, and unbeknownst to them, a differential equation is unrolling behind the scenes and generating a graph. Kind of how these things work, and I'll show an example of that here in a second. The advantage here, because you're using these high-level differential equation models and you're not modeling every individual, there's very few parameters. So if I had to model all of us in the room, I might need to know, the age of all of us, how much we've had to eat for breakfast, different things about our background in order to predict what each one of us are going to do, and then when we have will happen when we interact with each other. If instead I model the number of people in this room, all I really need to know is when does class start? When does class end? So there's very few parameters I have to model. And that's kind of what goes on in system dynamics modeling. But the disadvantage of that is that it doesn't cut, whereas I know that on average, this room's residence is going to climb at 10:30 and then fall at 11:45. It doesn't tell me about the student that comes in at 10:45, the student that leaves at 11:05. It doesn't tell me about those small scale variations. And if that matters, like if it matters that everyone shows up at 10:30 and they can't get through the door, and I care about kind of the flow into this room, then this isn't an appropriate modeling framework because it's just not going to capture that burst of traffic right at 10:30. It's going to capture on average that if I average over 100 days in this classroom, what does it look like at 10:30? Not at any particular day, is there a traffic jam at the door? And so that's kind of the big disadvantage there. So as an example of that, here's a system dynamics model of what's known as the Bass model of innovation diffusion in a marketplace. And so this is what SDM outputs often look like. They're drawn like these stocks and flows. So to kind of give an idea here, this box that says potential adopters, you can think of that as a state variable. And like this is an X and this is a Y. And you can think of this blue thing as a dx dt and a dy dt kind of linked together, where the negative derivative of this one is the positive derivative of this one. So wiring it up this way means that whenever you have anything leaving X, it goes into Y. And so if we model the rate of change of X, we're implicitly modeling the rate of change of Y. And so by drawing a diagram like this, which shows graphically this flow, we're effectively writing a differential equation. And then when you hit play, it solves that differential equation and plots X and Y over time. And so Frank Bass was a marketing researcher who was trying to understand the dynamics of how products get into the marketplace. Someone introduces an iPhone. How quickly they didn't have an iPhone back then, this is the 70s, but somebody introduces a new car or a new type of blender or a new kitchen appliance in general, and how quickly does it get into the marketplace, and does it penetrate all of the marketplace, and what can you do to increase the speed of penetration, and so on and so forth. So that's why he modeled things like potential adopters, people who could buy your product, and adopters, people who did buy your product, and how quickly you can turn potential adopters into adopters. And he had processes like word of mouth. So the idea here was that the potential adopters have to bump into an adopter and then they learn about it. And that's how they get it. It's sort of like an infection process. They get infected by it. And he had, extended versions of this where he added advertising in. He showed that advertising could kickstart this process, but ultimately you don't want to spend a lot on advertising. You can't count on advertising to do this conversion because it would cost way too much. But if you can use a little bit of advertising to start the word of mouth process, then that will end up sustaining the growth of the product and all that. So again, the point I'm getting here is not that we're talking about marketing, but this modeling process is not modeling an individual, like whether this person buys the blender or buys the iPhone. It's modeling a huge group of people who could buy iPhones and people who currently do have iPhones. And based on the number of people who currently do have an iPhone and the number of people who don't, how quickly does the iPhone market grow? And that is an example of a system dynamics model. So modeling these average trends over time. There are questions about that idea. So this is not what we do in this class, but I just want you as a contrast to know that it's out there and that it's a modeling framework that should be kind of aware of. If I wanted to see more of what one of these would look like, here's an example that I just borrowed from a this is an airport example. So this is an operations research example. So this is the case where system dynamics modeling is an operations research. Again, this is something we teach in 477. And so these three authors were interested in all of the things that cause airport delays. And so often the first thing you do in a system dynamics model is you just do a mind map of everything you think that might be a causal factor in the thing that you're studying, and then you draw causal relationships between them. So I'm not going to go through these, but you can kind of see like there's things like customs, military flights, airport size. There's all of these things that potentially are important, and then they've connected them with arrows. And if you look closely, some of them have pluses and some of them have minuses. So they have a positive causal relationship. If you increase one, it increases the other, or a negative. If you increase one, it decreases the other. And this is a so-called causal loop diagram. And it's called that because you look for loops. So you look for feedback patterns, and it helps you learn how to draw a stock and flow model like this one, which is similar to that Bass model, where you decide what your variables are. Those are these stocks. And then the big things coming into them are like pipes with valves, and then how the current stock level affects the current rate of change of other stocks. Each one, you write a little formula inside each one of these valves, which basically says, all right, if I do airport size plus the number of military flights or something like that, that is going to increase the number of delays we have right now. And so you'd write kind of a rough idea of how the delays change over time based on what these state variables are currently set to. And then once you have this stock and flow model, then you can hit go, and it gives you these average trends over time. So the average airport under certain parameters. And so they've here studied, they said, well, we've got a blue line where we took the parameters of the model and we made them smaller, and the red line where we took the parameters of the model and we made them bigger, and then the green line where we have our current set of parameters that are an estimate of our current airports. And this is sort of saying that as the market for travel increases, then the delays increase over time. But we can see that the increase in parameters causes a greater increase in delays on average, and the decrease in whatever these parameters are causes a decrease in delay in these trends on average. And so the suggestion from this paper is whatever these parameters are, which again, I'm not going to detail in this particular paper, that there would be a recommendation that if airports are interested in their average delays, then maybe they might be interested in pushing down what these parameters are. They're not saying on any given day that will reduce your delays, but they're saying on average over time that will decrease your delays. And that's what they are trying to model in the system dynamics model. So that's the type of output that you get here. All right, so the contrast to that is an agent-based model, where here you are modeling every single individual in your virtual world. So you're modeling people as they interact with other people. You're modeling people as they interact with the space that they're in. So when they step here, if this space has a particular property, the person can respond to that. So you're modeling all these microscopic interactions between people and space over time. And so they're often spatially explicit. So they're great for things where you want to know, where do people go? Do they all go in the corner? Do they spread out? Those sorts of ideas, boarding examples. So you want to model how long does it take to board a plane? And you can come up, and so Southwest Airlines did this, for example. So back in the 80s, everybody used to board from back to front. And then Southwest came out and they said, does it really matter how you board a plane? And the logic said, well, you should be able to, it definitely, you got to do back to front and outside in or whatever. And so Southwest then built agent-based models where they had little individuals go onto virtual planes, and they went to the back and they boarded back to front, and then they boarded all sorts of these other ways, and then they just boarded randomly. And then so they did a bunch of studies in virtual planes with several replications of these random individuals and these ordered individuals and so on. And what they found was it was a wash. is that it really didn't matter how you boarded that plane because, people would show up to the gate at different times, so they would get out of their boarding order. Some people would just take longer to get out of the aisles than others, all of their simulated people. And in the end, there wasn't that much of a difference between those. And that's when Southwest came up with their open boarding policy, which they've now sort of gotten rid of. But Southwest's open boarding policy, no, it's not totally open boarding. You could pay extra to be one of the first to get on. So they found a way to monetize it. So they said, we can have on-time departures and we can get a little extra money out of people who will want to pay to get on that plane first. And other airports or other airlines figured this out, and they also got rid of their structured boarding policies, but then kind of raised the ante even more to say, all right, we'll actually put different groups and you can pay to get into these different groups. So you're paying for a much more finer scale order. And now Southwest, as of a couple months ago, has decided to get rid of their policy and become more like a standard airline where they now, you pay sort of for a more fine-grained order. So they figured out a way that, maintains operations and they end up having more profit, all by using these agent-based models that kind of demonstrated them the feasibility that, maybe it doesn't matter how you board a plane. So that's an example of you had to model all of the individual interactions there. The advantage, potentially very realistic if you have a good model of those individual behaviors, but then that's kind of the disadvantage is that there's a large number of parameters that can be difficult to set. So yeah, I can model 1,000 people individually where every person does something a little different than every other person. But how do I know I've chosen the right 1,000 people to put into my virtual world? And so that becomes very difficult to defend. It also can be very slow to simulate. So if I'm just simulating a differential equation where I've got a number x, and that x is 1,000, and it's just a number, and the 1,000 goes up or down, then that's fast for a spreadsheet, for example, even to calculate. But if I have 1,000 individuals where each one I got to keep track of where they are, how they're interacting, who they're interacting with, what they do next, whenever they interact with certain types of people, it's just a lot more bookkeeping, and these models can be a lot slower to simulate. So, and then on top of all of that, sometimes you look at these models and you think, that's interesting, but you think, that's interesting in the same way you thought the real world system was interesting. So sometimes you don't actually get a lot of insight out of these models because they can be just as complex and ugly as the real world system you were trying to focus a lens on. So, it's kind of like if you look through a microscope and instead of focusing on an area, you just see the whole thing as if you didn't have the microscope, then why did you have the microscope in the first place? So that can be a problem with agent-based modeling as well. So examples of agent-based modeling, they can look kind of cartoony because, again, there's so many details that you're kind of limited in how realistic you can get, because then you end up, the sims take forever to run. And so you still try to simplify something. So you might be doing a traffic simulation where you simulate every car and different intersections, and you're trying to do different timing policies on kind of a generic road system. And then you study this over time to see, how many traffic jams I get, those sorts of things. You can have disease spread. So you can have individuals that are moving around randomly, and under what conditions, like quarantine conditions, et cetera, do I get the least amount of disease spread? Or, things don't have to be moving around. You can simulate networks. So you've got, generation, storage, and distribution of power. So you've got kind of a neighborhood of homes that are all connected to the same distribution station, and they all have different power use profiles. And you might want to study how is my storage policy and my generation policy making sure that I keep up to demand, given that their demand moves randomly. Every house has a slightly different demand and it changes throughout the day. So here, there's no spatial component, but there's this complex network that you have to implement. Another example of these things. So this is going to be a moving example, but this is, another airport example here, where this is what I'm going to suggest here in a second is maybe a better null model, but this is sort of the what if question of, well, what if people arrived randomly, just moved around an airport randomly, and they just arrived to these security lanes, moved slowly through the security lanes, and then went off to their gate. So they didn't actually get organized into special lines or anything. They just kind of bumped into these things. And you might say, well, what do you mean they moved around randomly? Well, that can be a model for them doing other stuff outside security. They stop at a store, they arrive at different times, and so on. Or like I'll say in a second, it can be kind of a null model of like, well, you might have had some crazy operational strategy here, but if it can't beat this, then your operational strategy for organizing people getting into these lanes is not going to be any good. So what a model like this would look like, if it will start on click here. Let me see this way. Well, in theory, this would be running. Let me just stop and restart the sim here, or the sim. All right, that I think is starting to run. Well, I may have to step through this. For some reason, PowerPoint's not running to run this in real time, but imagine, if you will, and I'll step through different snapshots, people bouncing around randomly here. And as they move into these different slots, then they get kind of captured by these lanes that are green, those are lanes that are open, and then they kind of move down through here and then eventually go off to their gate. So we can, turn on and off different queuing lanes and see how the number of queues affects how quickly people get to their gate, for example. So we can see if there's, say, diminishing marginal returns of the queues. So at what point does turning on another queue not really help people get to their gate any faster? At what point does maybe it does help them get to the gate faster, but it's not a good enough performance improvement to justify staffing that queue, and so on and so forth. And so it's yeah, it's unfortunate this isn't kind of running here. I guess I can try it one more time to see if I can inspire it to run. Maybe I'll try also stopping the share, restarting it here. All right, so an example of this ABM as it's running. So it's kind of cartoony, but you can see that you're getting variation. So the number of passengers currently going through the metal detector right now. So you're getting, moment by moment variation as opposed to just generally an average. Seeing the number of passengers cleared here. So you can see this mouse is moving around and turning queues on and off, and then watching how those queues affect these dynamics here. So again, it's getting this right and making it convincing is the hard thing. But if you do have a convincing story to tell about these microscopic interactions, then this is a very powerful framework, because you can simulate a very realistic looking world, right on your desktop. So that's the potential advantage of these things. Now, a common strategy is what I say is to use an agent-based model as a null model. So a lot of times it's not about making this the most realistic, but it's imagining, like, again, if somebody says, my fancy way to order people into these queues is much better than anything else you can think of, then you can say, all right, well, let's just see if we just randomly allowed people to hit these queues, what the performance would be like. And if your system can't beat that benchmark, that null model, then your system's probably not that great. Any other system would be fine. So in a lot of times, I'm not suggesting this is how we run an airport, but we use this as a benchmark for hypothetical ways to run an airport. Something we can do. All right, so any questions about that, agent-based modeling? This is something, and I think lab 4, I'm going to give you an opportunity to experiment with agent-based modeling, run 2 models and play with them. And then for labs 5 through lab 10, it'll all be discrete event system simulation. Yeah. So the question there is how do you know which model or which modeling strategy is better? So if it's down to within a modeling strategy, which operational idea, this queuing system versus this queuing system, that's going to be based on statistics. But if it's like, which one do I use right now? Do I use a system dynamics model for, is it better for system dynamics modeling or is it better for agent-based modeling? Then you have to sort of think about at what scale is the question that I'm asking. And so ideally, I would like to use the modeling strategy that's the quickest for me to run, the easiest for me to program, the easiest for me to maintain over time, and the best for me to communicate to my stakeholders. And that might be a system dynamics model, but a system dynamics model isn't going to capture these moment by moment variations. So if somebody wants to know, not on average what the throughput is through your system, but do I ever get a scenario where there's 1,000 people waiting? That one, that off chance that like most of the time you have 3 people waiting in line, but there's some pathological cases where if things are just right or just wrong enough, you could get like 1,000 people waiting. If you say, I would never, ever, ever want that to happen, a system dynamics model doesn't have the ability to make any predictions about that. But if you want to say, what are the cases in which I might get 1,000 people waiting in line, then you can run an agent-based model, or maybe even a discrete-event system simulation model, and have it run a bunch of different cases and find one of these pathological cases. And then you can say, aha, what happened on that one day where I had 1,000 people waiting in line? And it would say, well, when people arrived in just this particular order, it found this sort of weak spot in your system, and maybe that's where you want to target things. So it just kind of depends on what you're investigating, what questions you're asking. Great question. Any other questions? Okay. So this class is primarily about discrete event system simulation modeling, also known as process-centric modeling. It's a blend of system dynamics modeling and agent-based modeling. It's meant to be faster than agent-based modeling, more realistic than system dynamics modeling, and generally more comfortable to program in than agent-based modeling than say agent-based modeling, while still allowing you to trickle in more complexity than system dynamics modeling builds in. So the idea here is you're not modeling individuals making with agency. So that's an agent-based model, is you're modeling something that can decide what it wants to do next. In a process-centric or discrete event system simulation model, the things moving through your system are just like they're just like pinballs, or they're passive elements that are being pushed around from one box to another, and you're modeling the logic of how they move from one box to another. You're modeling the process. So each one of these individuals compete for finite resources, and they wait when the resources are not available. So they need to go from process 1 to process 2, but in order to go to process 2, it requires individuals already in process 2 to get out of process 2. So they wait in process 1 to get into process 2, but they don't have a choice in what they're doing with their waiting. They can't choose to go somewhere else unless process 1 decides that since process 2 is busy, I'm going to then move you into process 3. So you write the logic differently. You don't write it from in animal behavior, we have something called an Umwelt, which is like the sensory experience of the animal. You don't write the programming from the sensory experience of the agent. You write the programming from the kind of perspective of the process that the agents are sitting in, as if there's some sort of machine that is moving the individuals around from process to process. And so the key modeling parameters are how those passive individuals arrive to the system and how long each resource spends with each individual. The resources are the things that are inside the processes interacting with the individuals. And so how long an individual needs with a resource is an important modeling parameter. And the advantages of this, you can get more realistic than SDM because you do model individuals. It's faster to simulate than ABM because you don't have to keep up. Like, although you're modeling individuals, you're not giving each one of those individuals their own logic. The logic still sits in the processes. So you can see here that I could potentially have 1,000 blue dots in here, but I'm still only going to have 1, 2, 3, 4, 5 processes. So the logic, that the bookkeeping that I have to keep up with is I really only have 5 things I need to compute at every step. And the blue dots, those are the passive individuals. Those are just, variables that each one of these 5 things keeps track of. An agent-based model, if I had 1,000 blue dots here, I would have 1,000 little parallel processes running. And so that takes a lot more compute. So these are faster to simulate. They are often a good fit to engineered systems because in engineered systems, we often have a rigid process structure where we always know we have flow charts. We love flow charts. And so we can draw basically, in fact, you can go in to Visio, a Microsoft flowchart program, draw a diagram and import it directly into Arena, the tool we use, and turn it into a discrete event system simulation model. The disadvantage is if you have a really weird state-of-the-art system, like a totally unconstrained manufacturing system where there's a bunch of robots moving around, interacting with different parts of widgets and sort of like a chemical reaction network, building things up, then it can be difficult to put that into this type of framework because you don't quite know where things don't always go through exactly the same set of predefined trajectories. And on top of that, the programming here is going to actually require a little bit more background in stochastic modeling or modeling with probabilities. And we'll talk about what stochastic modeling is here briefly in a moment, and then I think next week. So it takes a little bit more of a specialist to use this type of modeling to capitalize on the advantages. But here's basically what it looks like. Like I said, you can draw a flow chart in a tool like Arena. This is drawn in an older version of Arena. And the idea here is that you can then add these realistic monitors to this flow chart and visualization. And the visualization allows you to visualize variables that are going on here that's going to make this look more like an agent-based model, even though the logic is a little bit closer to a system dynamics model. And you can even pop that visualization out into the 3D. So you've got this 2D that's going on up here is now being shown down here in 3D. And this is all in Arena. And so we can see as these individuals line up at this security, this document checker at an airport, they go through a process here where the process is they arrive at security, they wait a little bit at the document checker who checks their documents, they pass through security, or they get denied access. And because they arrive randomly, there's different times in between them. And because the document checker takes different amounts of time to check each one of their documents, so maybe based on different properties of the entities that arrive, or maybe based on just general randomness. Like sometimes it's quicker for them to do one check than others. Then you get this real-time variation, this minute-by-minute variation that's going on here. And so you still get variation like you get in an agent-based model, but you don't have to model each individual agent. You just model the stations that they stop in. And so it's got kind of a mix of both worlds. So this is an example for this airport case. So it's not spatially explicit, but we can visualize the airport as if it was a spatially explicit agent-based model. So although it's pretty obvious that these individuals aren't walking all over, it gives our stakeholders the impression that this is a feasible trajectory. And so they can say, okay, I can imagine, I don't need this to walk everywhere, but I can see that, they could line up like this. I could imagine a reality where this trajectory could happen. And so that's where the visualization can help, but we're not actually formally spatially explicit like we would be in an ABM. I think this emergency room example is another great version of this, where and I'll show you the logic in a second, is got very simple logic, but the visualization here makes it look a lot like an agent-based model. You've got these cars that are showing up to this area here. They're going into the reception area. They're talking to this receptionist that sends them to a waiting room. Eventually, the waiting room individuals go into the emergency room. If a bed is available, they get assigned to a bed. They stay or actually, there's a waiting room on the inside, and then they get assigned to a bed. The beds are occupied for a certain amount of time and then maybe need to get cleaned. And then eventually those individuals move out. But you can see sometimes these beds turn red. So some individuals are in worse shape than others. And so you can get triage situations going on. So there's a lot that can go on here. And it really looks like an agent-based model. It looks like a real hospital trajectory here. But if we start zooming in on, you get real variation out. So the number in the system here, this looks kind of realistic. This is the breakdown of the types of individuals that have gone through that emergency room. So some are critical, some are serious, some are fair, so on. This is our utilization. So how many beds were used on average, and so on and so forth. So a lot of variation that looks like a real hospital room. But the process flow is pretty simple. Like, if I look up here, from the patient rooms, what's the process? Well, you first secure a bed. There's a little bit of a delay as that room gets prepped. You have to secure a nurse. There's a delay to wait for that nurse to show up. You got to secure a doctor delay. Once you're finally done with the doctor evaluation, then release from the hospital, calculate the total time in, calculate the throughput, and get rid of the entity. So every entity that manages to reach a doctor goes through this exact same history from the point at which they go from a patient room out. So it looks like there's a lot of variation there because there's variation in the timing. But once you hit the patient room, we know that the timing will be different, but the order will be the same. Same thing down here, Gesundheit, is that there's this triage area that they go into, and they go through evaluation. Then there's a branch. They either can be admitted or not, and then be routed to the next stage. So these are relatively simple programming tasks here, just diagramming this flow, and it's focused on the process. It's focused on where the individuals are and not what each individual is doing, which makes it so much easier to use. Likewise, with the airport security example, you can add embellishments, and so now we can say, did they pass security fine? But after they go through security, they need to secure a resource for the X-ray machine. And then every 15 of them, they actually go through additional security checks, and everybody else gets cleared here. So you can, these are still a relatively simple model flow. So adding complexity, this does totally change the system and allow us to study more things about it. But we're just bolting on a few more process steps. So it's not that intimidating. And we get, useful variation out of it. So we can study the waiting time. So across all of these individuals, then we end up, seeing that there's an average waiting time at this particular queue that has a half width. And so that's, implying that there is significant variation across all of the individuals that waited in this queue. And we can aggregate things in different ways. How long did they wait in this queue? How long did they wait in this queue? And so on and so forth. So we can really, look down in a very fine-grained way of different statistics that across the sim that are generating this realistic variation, which makes it so powerful. And different metrics, not just waiting time, but utilization, not just utilization and waiting time, but also cost. So you can say, every time I staff a security officer, it costs this much per hour to staff them. How many hours did I staff that security officer, multiplied by the hourly rate, and it automatically does the bookkeeping for you. Busy costs. So this is how much useful time I spent, $5,000 staffing security officers that were checking passengers, but they're not 100% utilization. So I spent $760 paying security officers to just stand there idle. So, you can get those stats out of here as well. So a lot of cool things you can do, useful in a wide range of industrial applications for sure, but you also see it pop up in not necessarily industrial applications. So this was a paper from 2016 where they used ARENA to model a gleaning process at a food bank. And so they were trying to figure out how to staff volunteers. The volunteers kind of show up randomly. You don't know what volunteers you get every day. You don't know what farms are going to have food available for gleaning every day. And how do you match those two things up together? And they tried different strategies in an ARENA-based model here to optimize this gleaning process to maximize the output from this. And so this was the model that they built. Looks just like some of the models that I was showing there. And this flowchart model inside ARENA looks just like this high-level flowchart that they drew in the paper. So you can kind of start things without worrying about ARENA and then just translate them into ARENA or FlexSim or Simio or whatever. And, and you don't have to model all the details of every single volunteer and every single farmer. You model like how many volunteers we have, kind of like system dynamics modeling, but it allows for more texture, more complexity, and so on. So a lot of cool things that you can do with these discrete event system simulation models. So any questions about that? The three types of sims. Okay. So let's do an iClicker question. And so open up your iClickers and I'll start a short answer poll. And the question is, what of the three types of simulation do we primarily study in this class? Which of those three? You can put it in a abbreviation form. You can put one of the terms I gave, but however it shows up in your head, there were three types of sim: agent-based modeling, ABM. There was discrete event system simulation modeling or process-centric modeling, DES, and then there's system dynamics modeling, SDM. So of those three, what's the one that we primarily study in this class? Just as your flag that you were here today. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right, I'll leave it open for a couple more seconds. So again, ABM, DES, or SDM. All right, I think that's about everybody. And I got, I think generally the results that I'm seeing here are consistent with what I was hoping for. So I'll go ahead and stop the poll. I was looking for DES, of course. About everybody got that. So process-centric modeling or discrete event system simulation modeling. Okay. All right. We're not working with Arena just yet. That will be not until Lab 5. But if you are interested in installing Arena yourself or trying it out, that's totally fine. Just note that unless you have the most recent version of the textbook that was released this year, then all the textbook examples, and actually a lot of the examples that you see in the screenshots for the lab are going to look a little differently. So before the most recent version of Arena, things looked like this. Now they look like this with a ribbon across the top here. So the elements referenced in the book are located in slightly different places. So you notice like these boxes over here, which we'll get to when we get to Arena closer to Lab 4, they have like this basic process block. There is no basic process block anymore. So all of these panels have been renamed and the block's been resorted into different panels. But once you get used to where you have to look, then it ends up being pretty easy to translate from one to the other. But it's just something to look out for, is that things are going to look different if you look at some of the materials in the textbook and in the book, and then versus what Arena looks like right now. But again, you don't have to worry about Arena for another couple of labs. More information on installing and using Arena can be found on Canvas. Look under the course information. There's a section on the software used in this course if you're interested in installing Arena or just getting access to it remotely or in the labs. All right, so now let's cover some of those modeling terms that you used in the first lab, as well as what you'll need in the first homework. So I've been talking about a system. A system is just a group of objects connected for some joint purpose. So it's a pretty broad definition. We have to define the boundary of a system, which is basically what we leave in and what we leave out. So the more generalizable a system often means the narrower the boundary. We leave a lot of stuff out. More specific a system, we throw more stuff in. So it's really important for us to decide what the boundary of our system is. A dynamical system is a specific type of system where we're not just interested in what the relationships are, but we're interested in how the system changes over time. And that's what we study in this class, dynamical systems. And so this is a system that can be observed as it changes over time. And in these systems, we use the word state to represent what the current system is doing at an instant of time. So we have, an example state is there's 5 passengers currently waiting in line. Currently, right now, 5 is the state, 5 passengers, while 2 out of 3 agents are busy checking. So the state of the whole system is 5 passengers waiting and 2 agents checking ID. We can say the state of the waiting line is there's 5 passengers in it. So state is a number, but state variable is the thing that we store the number in. And so we're going to throw around these terms. If I refer to a state variable, it might be X or Y, or it might be a phrase, number of passengers waiting in line. So the phrase, number of passengers waiting in line, isn't enough for me to know what's going on in the system. It just tells me what I'm keeping track of in the system. If I say there are 5 passengers waiting in line, then at that point, I know, okay, at the next instant of time, there might be 6, there might be 4. It allows me to start predicting what's going to happen next. So it's the snapshot of the system is the state. The things that the snapshot goes into are the state variables. That distinction makes sense? Anybody have any confusion about state variable versus state? Okay. All right, so then in DES specifically, so that was systems and then specifically dynamical systems. Now in discrete event systems, which are a type of dynamical system, we have things called resources. These are things that are in limited quantity. They do not come and go. They can break down and there can be more of them that become available, but they aren't flowing through the system. But they are the things that are needed for system work to get done. So they perform activities. And so, an example is in order for you to go through a checkout lane at a grocery store, you might need a cashier or a kiosk. Well, if that cashier goes on lunch break, then you just have to wait. You can't get out of the store. That cashier is a resource. She can go away or come back, but that cashier is not the thing that is leaving the store. At least in our model of the store system, we don't care about when the cashier arrives to the store and leaves the store. We care about whether that cashier is available to do work at any instant of time, and that makes that cashier a resource that causes entities, which is something I'll define in a second, to wait before they can leave the store. So examples, X-ray scanners, TSA officers, boarding pass kiosks, airplanes. These are all things that we think of that are ever present in our system. They might become unavailable, but they're still there. Their ghost is still there. And they delay entities. These are the things that arrive into our system, do something with our system, and then leave. So if I'm modeling a grocery store, usually my entities might be the customers that arrive to the store, spend a little bit of time shopping, and then leave the store. And we could study, how many items did they buy? How long were they there? How long were they at the cashier? And so on and so forth. When they arrive to a resource and the resource is not available, usually because another entity is using it, they have to wait for an amount of time, and that's referred to as a delay. So this is the first important distinction I want to highlight. Activities versus delays. The time you spend in or with the resource is an activity. That's something we know ahead of time. We know, statistically speaking, a cashier, if somebody has 5 items in their cart, statistically speaking, without simulating the system, it will take a cashier an average of 2 minutes to check them out, maybe plus or minus 30 seconds. That 2 minutes plus or minus 30-second distribution, we know ahead of time. And that makes it an activity. But if there's somebody arrives and the cashier is already being used, we don't know if there's 6 or 7 people in line. we actually don't know how long the seventh person is going to wait until they get to the cashier, because it depends on all these random things adding up in front of them. And so that, because we need to simulate it to figure it out, is what we make it a delay. So an activity is what we're going to end up calling an input, and a delay is what we're going to call an output, because we know the activities ahead of time, and we have to simulate to figure out what the delays are. Are there questions about, there's an example here of entities. Are there examples about this, or questions about this distinction? Activities versus delays. Activities are inputs. We know them before the sim. Delays are outputs. These are waiting times that we can only know after we've simulated the process. Okay. Attributes. Entities can differ from each other, and the way they differ is they differ by their attributes. So you can have this entity came to the store to buy one item. That's their attribute. What are they here for? They need to buy Zyrtec because they have allergies, and that's it. This entity arrived to the store because they needed to basically outfit their whole fridge. And so they're there to buy eggs, bread, lunch meat, which right now there's a lot of listeria going around, so don't buy lunch meat, and so on and so forth. So there's a bunch of things that this other person, came to the store, and one would imagine then that the one who's only buying one thing is going to take a lot less time in the store than the one who's buying a lot of things. So the attributes can change how long the entities reside in each one of the processes, using up some of the resources. So attributes are one of the things that makes entities differ from each other. Examples of that: whether someone's a TSA pre-check status, when they arrived at the airport, the number of times. This is something an attribute can change over the system execution. So you can keep track. This entity has had to get rechecked through security 5 times so far. They're really unlucky. Well, maybe as they increase the number of times they go through security, we're going to prioritize them. So if you've already been through security once, then maybe you don't have to wait in line. So we will grab you out of the queue based on this attribute, which we can change while we're running the sim. And then activity versus delay, just emphasizing this: activity is an input, delay is an output. Any questions about these terms? The terms we're going to use all semester as we talk about discrete event system simulation models. Okay. So example, manufacturing system, entities might be parts that flow in and out of it, attributes, the features, how many parts there are, what color, when they arrived. When they arrive to the manufacturing system, they have to wait for machines to assemble them. And it might be that you have a blue part has to wait for a red part, and they have to come together in this machine. And if you don't have blue, red, and green together, then you can't assemble this widget that comes out. And so they might all have to wait on each other. So that can also generate a delay. So you can be delayed because the machine is busy, or you can be delayed because the machine isn't ready because another type of entity hasn't arrived yet. So that's a resource here. Each one of these things are entities, and each of these are resources. So are the people handling them. Those are resources. The activities are how long it takes to actually, once you get into the machine, how long does it take for the machine to assemble you into the widget? The time it takes for you to wait to get into the machine, that's a delay. Events, so these are points of time that change the state of a system. Whenever a part arrives to the system, the state of the system increases by 1. Whenever a part departs the system, the state of the system decreases by 1. At any instant of time, you get a change in the state of the system. We call that an event. Events can also be failures. When this machine dies, which it can randomly just die, that is an event. Then suddenly we have one less machine, and everything waiting on this machine just has to keep waiting and waiting. Process completion, part arrival, kind of cover those. State variables, the variable here could be for every machine, the variable keeps track of whether it is idle or busy, whereas the state is actually this machine is idle right now, or this machine is busy. So the state of a 5-machine system at a given time might be this combination of 3 busies and 2 idles, whereas the state variable is going to be these variables we use this for the bookkeeping of keeping track of the state. And that's our little manufacturing example. So why are some machines idle? Why aren't they always busy? Well, because machines only do work when there are widgets that arrive. And if you have to wait, if a red and a blue widget can't go into the machine until a green widget arrives, then you just got to wait for the green widget to arrive, and that will mean the machine will be idle. Question? That's an interesting question. So it uh, generally that would be I would call like a performance variable. That would be something that would be like a KPI. It'd be a key performance indicator, unless there is logic that based on the number of parts that have been produced, it changes the flow. So if for some reason your manufacturing system is adaptive, then you do need that state variable to say, okay, we only need to build 50 parts. Once we build 50 parts, we stop building widget A and we become widget B. Then you need a state variable. Great question. Any other questions? Okay. All right. Other example here, and just for time, I'll just kind of spit it all out here. But university example, students would often be modeled as the entities. They have different attributes. These are all the different ways that students can differ from each other, and not only at a large time scale, but short time scales. So students enter classrooms at different times. Classrooms are resources. So there could be students waiting to get into this class right now, but they can't because they can see that this class is occupied. And so this classroom becomes a resource that is busy right now. Instructors become a resource. We can't start class until the instructor arrives. And so on. The time of a class, like nominally it's 75 minutes, but sometimes it's 50, sometimes it's 76. So, but we know that ahead of time, that we know the average time of a class, but the delays, how long you spend waiting outside the class, then that might be something that we don't know unless we actually simulate the system, and we do a bunch of simulations and take stats over those bunch of simulations. The events that change the states: students arrive, class begins, class ends, there's a fire alarm. All these things can change the configuration of the system, and thus their events. And then state variables, these are the bookkeeping variables: classroom, instructor, number of students. And then the actual things you load into those variables are our states: busy or idle, lecturing or proctoring, 0 to 104 or 135 or whatever. Okay. Questions? All right, so when you start drawing these flowcharts, then those terms that we just said will show up in this particular way. So we've got these symbols, like this symbol here generally means that it's the thing that generates the entities. So entities arrive here. So when we drop this symbol onto a chart and drill down into it, that we'll be asked, what is the time in between the entities? What distribution does that come from? How many entities should I generate maximum? Those are the types of things we have to model by putting into here. Those are the inputs for this. Processes, so the square blocks here, the rectangular blocks, that's where entities meet resources. So when we drill into this, we have to say what resource is being used, or resources, and when entities match with them, how long do they stay matched in there? And that also can be a random distribution, but that's known ahead of time. And you drill down into this before you write the sim, and you put that activity information into that process. These diamonds are branches. And so entities will come in one side. And so they come in one side, and then they can come out the other sides. And you can have a logic in here that allows them to say, well, if this entity is of a certain age, then they go to a priority lane. If this entity has a certain status, they go a certain way, and so on and so forth. And so you can have them take different paths. And then ultimately, the entities have to go somewhere. And so there's this block which disposes of them and might keep track of stats like how many entities were disposed of. So that's what you have at the end of your sim. So as you build your sim, you draw the diagram first, and then you drill down into each one of these blocks. You set up the resources and activities, you set up the entity arrival times, you set up the branching logic, and then you're ready to hit go and then watch your simulation. And that's basically, once you figure out how to find these 4 blocks, I mean, there are other blocks too, but those other blocks are implemented with these 4 blocks. Once you go into Simio or FlexSim or Arena or AnyLogic or whatever, once you find these 4 blocks, you're off to the races. Every discrete event system simulation software is basically implementing these and giving you ways to collect stats on those. And the events, those will be generated here. Someone arrives, a process finishes, so on. That's an example we've already seen from Arena. Looks just like these. So a stream of passenger arrivals, the time it takes to actually check their ID, whether they pass security or not. Because there's only one person checking ID, then passengers may have to wait for that one person to become available. And some passengers exit cleared and some passengers exit denied. And events, the events here, passenger arrives, events, ID checking begins, ID checking ends. So at the end of an ID check, that allows a new passenger to move into the resource, which causes the line to change how many people are in it, what makes it an event. So there we go. All right, any questions about those examples? Well, the only other thing that I want to cover in the last minute here is just this term stochastic. And then we're going to come back to this in later lectures. And I might just jump ahead here to this slide here. And this will become more clear as we start building these models. But I've mentioned a couple of times that activities can be random distributions. Stochastic modeling, which is what we use in DES, are models that use randomness instead of deterministic rules. And so stochastic is a Greek term for guessing or conjecturing. It doesn't actually mean random. It means I'm going to make a guess that the natural process is random, even though it's probably not, or I actually don't care if it is. But it will be easier for me to model it as a distribution with variance than to try to get all the details right and what actually causes that variance. And that's what we mean by stochastic. We don't care if the behavior is fundamentally random, but we model it as if it is. And that reduces the modeling burden. It makes our models simpler. So this is simulating stochastic systems. That's what we mean by stochastic. And that's actually a good spot for us to stop. So I'll give you one last attendance exercise here. And so I'll do this one. And I'll start this poll. I'll do another short answer. Poll started. And so the question I have for you here is, what is the DES term we use for the instant of time that a state changes in a system? So what is that term? So it's a one-word term that we use that for the instant of time when a state changes. So is it activity? Is it delay? Is it entity? What is that one word for the time, the instant of time when the state changes? And that's all I've got for you. So if you have any questions, let me know. Otherwise, have a good weekend, and we'll see you on Tuesday.